Hello friends, welcome to my lecture on review of integral transforms 3. This is third and final lecture on the review of integral transforms. Let us look at the Fourier integral. We know that the Fourier series are powerful tools in treating various problems involving periodic functions, but many practical problems do not involve periodic functions. Hence, it is desirable to generalize the method of Fourier series to include non-periodic functions. Let us consider two simple examples of periodic functions of period t and see what happens if we let t tends to infinity. Consider this function f(t(x) equal to 0 when minus t by 2 is less than x less than minus 1, 1 when minus 1 less than x less than 1, 0 when 1 less than x less than t by 2, and the period of the function f(t(x) is t which is more than 2. Then we can look at the graph of f(t(x). This is the graph of f(t(x). You can see it is periodic function, and here we are in the example we are taking t to be greater than 2. So, let us consider t to be 4. So, over the interval minus 2 to 2, okay. Over the interval minus 2 to 2, you see that from minus 2 to minus 1 f(t(x) is 0, then f(t(x) is 1, from minus 1 to 1, then f(t(x) is equal to 0 from 1 to 2, and it has been extended periodically over the whole real axis using the periodicity t equal to 4. Here we take another value of t, say t equal to 8, and then you see the graph of the function f(t(x) from minus 4 to 4. This is 0 from minus 4 to minus 1, minus 1 to 1 it is 1, and then 1 to 4 it is 0, and then it has been extended periodically by using the period t equal to 8. When t tends to infinity, what happens? Over the interval minus 1 to 1, the graph is f(t) equal to 1, okay, as t tends to infinity, while over the remaining values of x, from x equal to 1 to infinity, f(t(x) tends to 0, f(x) becomes 0, and then from minus infinity to minus 1 it is again 0, and you can see that it is not periodic, okay, with any period. So, when t tends to infinity, we obtain a function f(x) which is not periodic, because f(x) becomes 1 when minus 1 less than x less than 1 and 0 otherwise. Now, let us look at another example. Let us say f(t(x) equal to e to the power minus mod of x for minus t by 2 less than x less than t by 2, and f(t(x) equal to f(t(x) plus t equal to f(t(x). So, this equation tells us that f(t(x) has the period t. When t tends to infinity, we get the function f(x) equal to e to the power minus mod of x. f(x) is the limiting function of f(t(x) as t goes to infinity. As t goes to infinity, this interval tends to minus infinity to infinity, and f(x) becomes e to the power minus mod of x, and you can see that it is no longer periodic. f(x) is equal to e to the power minus mod of x. We have the graph of this function. Here you see e to the power minus mod of x, okay. E to the power minus mod of x is an even function from minus t by 2 to t by 2. So, this is the graph of the function, okay, from minus t by 2 to t by 2, and then it has been extended periodically by using the period t. Now, here what happens when t tends to infinity, okay, we have the graph of e to the power minus mod of x like this. So, you can see that it is not periodic anymore. Now, let us consider, so we have to see what happens when f(t(x) tends to say function f(x) as t goes to infinity, then what will be the representation of f(x). So, that is our problem. Let us consider any periodic function f(t(x) with period t, then we can represent it by a Fourier series. Let us assume that x is a point of continuity of f. So, f(x) is equal to a naught by 2 plus sigma n equal to 1 to infinity a n cos omega n x plus b n sin omega n x, and here omega n is 2 n pi over t. Now, when we let t goes to infinity, let us assume that f(t(x) tends to f(x). We further assume that this function f(x), the limiting function f(x) is absolutely integrable, that is the integral over minus infinity to infinity mod of f(x) dx exists. Then this Fourier series, by using the values of the Fourier coefficients a naught, a n and v n in terms of the integrals, okay, and taking the limit, what happens is that we get the f(x) as this integral 1 over pi integral over 0 to infinity a omega cos omega x plus b omega sin omega x dx d omega, where a omega and b omega are given by these integrals omega a is minus infinity to infinity f v cos omega v dv, and v omega is integral over minus infinity to infinity f v sin omega v dv. The integral on the right hand side of 1, this integral, okay, the integral on the right hand side of 1 is called the Fourier integral of f. The sufficient conditions for the validity of this representation of f x by the Fourier integral are given in the following theorem. So, if f x is piecewise continuous in every finite interval of the real axis and left and right hand derivatives exist at every point, and f is absolutely integrable, that is integral over minus infinity to infinity mod of f x dx is less than infinity, then f x can be represented by a Fourier integral. So, at a point of discontinuity, the value of the Fourier integral is equal to the average of the left hand and right hand limits at that point, like we have seen in the case of Fourier series representation of a function f, that at the point of discontinuity the sum of the Fourier series is average of the left hand and right hand limits. So, here also at a point of discontinuity the value of the Fourier integral is equal to the average of left and right hand limits. At each point of continuity the Fourier integral is equal to f x. Now, if notice that if f is an even function in the interval minus infinity to infinity, then the value of b omega is given by this integral. So, if f is an even function, okay, then f is an even function and sin omega b is an odd function. So, the product will be an odd function and therefore, b omega will be equal to 0, and when b omega equal to 0, the cosine terms will remain while sine terms will vanish. So, we will have, and the a omega will become 2 times 0 to infinity f b cos omega v dv, because cos omega b is even function. So, f b into cos omega v will be even. So, we will have a omega equal to 2 times 0 to infinity f b cos omega b. So, here when f is an even function, the Fourier integral representation of f contains only this cosine terms. This is sine term is not present in the Fourier integral representation. Similarly, if we have f to be an odd function, then a omega is equal to 0, because f is odd, cos omega b is even. So, the product is odd, and b omega becomes 2 times 0 to infinity f b sin omega b dv. So, here then in the Fourier integral representation of f only sine terms remain, the cosine terms vanish. So, b omega becomes this, and the Fourier integral representation is containing only sine term here. The integrals 2 and 3, these two integrals, integral this 2 and integral 3 are called this integral 3 and this integral 2, they are called as Fourier cosine and Fourier sine integrals. This one is called Fourier cosine integral, f x equal to this is called Fourier cosine integral, f x equal to this is called Fourier sine integral of f. Now, just as in the case of half range Fourier series, if a function f is defined over the half range, say 0 infinity, then over the interval minus infinity to 0, we can define it by using the even extension or the odd extension, and then we can find the Fourier integral representation of the function f, like in the case of Fourier series. So, here we notice that the representation of a non-periodic function f x given by this equation 1 is similar to the Fourier series representation of the periodic function f. Here also you can see we have a omega cos omega x, b omega sin omega x, like in the case of Fourier series, but there we have summation, here we have integration, that is the difference. So, range is now minus infinity to infinity and the summation has been replaced by integration. Let us find the Fourier integral representation of the function f x equal to 1 when mod of x is less than 1, 0 when mod of x is greater than 1. You can see that f is piecewise continuous on every finite interval, and moreover that integral over minus infinity to infinity mod of f x dx, this is equal to integral over you can see this function is an even function, okay, f is an even function, and first we reduce the interval minus infinity to minus 1 to 1, because everywhere else it is 0. So, mod of f x dx, and mod of f x takes value 1 when mod of x is less than 1. So, we get here minus 1 to 1, 1 dx, this is equal to 2 and which is less than infinity. So, f is absolutely integrable. Furthermore, f is having left hand and right hand derivatives at each point of the real axis. Okay. Now, let us recall the definition of the Fourier integral f x at each point of continuity. Let x be a continuity point. So, f x equal to 1 over pi integral over 0 to infinity a omega cos omega x plus b omega sin omega x d omega. Let x be a continuity point of f. So, then the Fourier integral becomes equal to f x. Now, here we see that b omega, f is an even function. Okay. So, b omega is equal to 0 to infinity f b sin omega b db. Okay. Since f is an even function, sin omega b is an odd function. So, the product of even and odd is odd, and therefore, this is minus infinity to infinity, minus infinity to infinity. So, this is equal to 0 and a omega becomes 2 over 2 times integral 0 to infinity f b cos omega b db. Okay. So, we get this 2 times f b into cos omega b db, and let us use the value of f. F is equal to 1 over the interval 0 1, and elsewhere 1 from 1 to infinity it is 0. So, this is 2 times 0 to infinity 1 into cos omega b db, and we get it as 2 times sin omega b over omega. Okay. 0 to 1 because it is 1, it is 1, 0 over the interval 0 1 it is 1. So, with this 2 times sin omega over omega. Okay. So, thus f x is equal to 2 over pi 0 to infinity a omega is 2 times sin omega over omega. So, this is sin omega over omega 2 we have written outside into cos omega x d omega. This is the Fourier integral representation of f at each point of continuity of f. And if you look at the interval minus 1 to 1, it is discontinuous at minus 1, it is discontinuous at 0, it is discontinuous at 1. So, the points of discontinuity are x equal to plus minus 1, not 0. At x equal to 0 it is continuous. So, this is our points of discontinuity. So, at from the points of discontinuity, the sum of the Fourier series is equal to the average of left hand and right hand limits. Now, at the point minus 1, left hand limit is 0, right hand limit is 1. So, average is 0 plus 1 divided by 2, that is 1 by 2, and at 1 the left hand limit is 1, right hand limit is 0. So, again average is half. So, we have 2 over pi 0 to infinity sin omega x sin omega over omega, and when x is equal to 1, cos omega x is cos omega, when x is minus 1, again cos omega x is cos omega. So, at x equal to plus minus 1 sin omega over omega cos omega d omega, this is equal to f x is equal to half. So, we can say that integral r, you can say integral 0 to infinity sin omega cos omega d omega divided by omega is equal to pi by 4. So, let us see so the integral 0 to infinity sin omega cos omega x over omega d omega, this is equal to pi by 2 when mod of x is less than 1, because when mod of x is less than 1, f x becomes equal to 1. So, integral 0 to infinity sin omega over omega cos omega x d omega is pi by 2, at x equal to plus minus 1 the value is pi by 4, and when mod of x is greater than 1, this f(x) is equal to 0. So, integral 0 to infinity sin omega over omega cos omega x is 0. In particular, when we take x equal to 0, you take x equal to 0, then at x equal to 0 f(x) takes value 1 and it is a point of continuity. So, 1 equal to 2 over pi 0 to infinity sin omega over omega cos omega x becomes 1 and therefore, the value becomes 1 equal to 2 over pi 0 to infinity sin omega over omega d omega at x equal to 0. It is a point of continuity and this gives you 0 to infinity sin omega over omega d omega equal to pi by 2. Okay, so you can see we can find even some improper integrals by using the Fourier integral representation of a function f. Now, let us discuss the inversion formulae for Fourier transforms. We may write equation 1 as let us put the values of a omega and b omega in this Fourier integral representation. Then we will have f(x) equal to 1 over pi 0 to infinity minus infinity to infinity. A omega becomes fb cos omega b dv. So, we will have fb cos omega b into cos omega x, and when you put the value of b omega you get fb sin omega b into sin omega x d omega. So, using cos a cos b plus sin a sin b equal to cos a minus b, we have this expression integral over 1 over pi integral over 0 to infinity minus infinity to infinity fb cos omega x minus b dv d omega. Now, by substituting the values of a omega and b omega. Now, here better let us look at this function cos omega x minus b. It is an even function of omega. The integral over omega is from 0 to infinity. So, we can make it from minus infinity to infinity and divide by 2 because of the fact that cos omega x minus b is an even function. So, this becomes 1 over 2 pi minus infinity to infinity minus infinity to infinity fb cos omega x minus b dv d omega. Now, let us look at the fact that sin omega x minus b is an odd function of omega. So, if you calculate this integral over minus infinity to infinity fb sin omega x minus b dv d omega, then because this is an odd function, integral over minus infinity to infinity with respect to omega will be 0. So, the whole thing will become 0. This is iota. So, 0 equal to iota by 2 pi and then this expression we have. Now, we add the equation 5 and equation 6, okay, this equation 5 and the equation 6 and use the formula e to the power I theta equal to cos theta plus I sin theta. When we use this formula, f(x) becomes equal to 1 over 2 pi integral over minus infinity to infinity fv e to the power I omega x minus b. Instead of theta, here we have omega x minus b. So, this is known as complex form of the Fourier integral. Now, we may write this equation in the following manner: e to the power I omega x into x minus b. Let us split into two parts, e to the power I omega x into e to the power minus I omega b. The integral inside integral is with respect to b. So, e to the power minus I omega b will be kept inside. E to the power I omega x contains omega. So, with this we can take outside the integral with respect to b, and then what we have 1 over 2 pi integral over minus infinity to infinity e to the power I omega x integral over minus infinity to infinity fv e to the power minus I omega b dv d omega. Now, this can be written as 1 over root 2 pi integral over minus infinity to infinity f omega e to the power I omega x d omega, where f omega is defined as 1 over root 2 pi. This I split into two parts, 1 over root 2 pi into 1 over root 2 pi. 1 over root 2 pi comes with 1 over root 2 pi comes with f omega, and the other 1 over root 2 pi goes with the remaining integral. So, f omega equal to 1 over root 2 pi minus infinity to infinity fv e to the power minus I omega v dv. Now, this representation, okay, is called as the Fourier transform of the function f. So, the f omega is called the Fourier transform of the function f, and the function f(x) given by 1 over root 2 pi minus infinity to infinity f omega e to the power I omega x d omega is termed as the inverse Fourier transform of f omega. Now, some authors will take here 1 instead of 1 over root 2 pi, and there we will take 1 over 2 pi while we use the inversion formula for Fourier transform. So, there is no ambiguity in that, because we generally use these Fourier transforms to in the practical problem, that is the heat conduction problems or other problems. So, there first we apply the Fourier transform, and then we apply the inversion formula for the Fourier transform. So, if we multiply here by 1 and here we take 1 over 2 pi, it is the same thing, because if you take 1 over root 2 pi in f omega and then while inverting you take 1 over root 2 pi, then also the result is the same. In a similar manner, we can obtain from equations 2 and 3. Let us look at equation 2 and 3. Yes, from here. So, this is f x equal to 1 over pi 0 to infinity f a omega cos omega x. So, we will get here as we will get it as into two parts. Let us take it. So, we will have, if you put the values there in equation 2 and 3. Yes. So, in equation 2 and 3 we have Fourier cosine, Fourier sine transforms. We have f x equal to 2 over pi. See, we get the Fourier cosine integral and Fourier sine integral by assuming f to be even and odd. So, from that representation f x becomes Fourier cosine integral 2 over pi 0 to infinity f b cos omega b db d omega. This Fourier cosine integral. So, you can break it into two parts, root 2 over pi 0 to infinity and then root 2 over pi 0 to infinity f b cos omega b db into d omega. So, what we do is and then cos omega b and then cos omega x also. So, cos omega x will be written here, and what we will get root 2 over pi integral 0 to infinity f b cos omega b. This quantity is termed as f c omega. So, we will get under root 2 over pi 0 to infinity f c omega cos omega x d omega. So, this f c omega is called as the Fourier cosine transform. This c denotes a cosine transform. Fourier cosine transform of f x. And this f x equal to root 2 over pi 0 to infinity f c omega cos omega x is called as the inversion formula for the Fourier cosine transform. Similarly, for Fourier sine integral, Fourier sine integral we have f x equal to 2 over pi 0 to infinity f b cos omega x omega b into cos omega x dv d omega. And in the similar manner I can write it as root 2 over pi 0 to infinity f s omega sin omega x d omega, where f s omega is given by root 2 over pi 0 to infinity f s omega. F s omega means Fourier sine transform. So, these are this is Fourier cosine transform, this is Fourier inversion of formula for Fourier cosine transform, this is Fourier sine transform, this is Fourier sine transform, and this is inversion formula for Fourier sine transform. Now, these equations give the inversion formulae for the Fourier cosine and Fourier sine transform of f. In some authors, as I said, in the case of Fourier transforms, here also some authors take here 1 and here 2 over pi, here 1, here 2 over pi. I have taken root 2 over pi, I have split 2 over pi into 2 parts, root 2 over pi, root 2 over pi, but there is no ambiguity if you take 1 here and 2 over pi there. So let us solve this equation 0 to infinity fx cos omega x dx. This is an integral equation because the unknown function fx appears under the integral sign. Now let us note that this is nothing but the Fourier cosine transform of the function f. Let us look at this Fourier cosine transform. This is f c omega root 2 over pi 0 to infinity f v cos omega b dv. So let us take, instead of root 2 over pi, let us take 1 here, then f c omega is 0 to infinity f v cos omega b dv. Let us solve this integral equation. This is an integral equation because the unknown function fx appears under the integral sign. If you look at the integral, it is 0 to infinity fx cos omega x. So it actually gives the Fourier cosine transform of the function f. If you look at this expression f c omega root 2 over pi 0 to infinity f v cos omega b dv. So if you replace this v variable of integration b by x, it is 0 to infinity fx cos omega x dx. So if you so what we do is let us take the coefficient here root 2 over pi as 1. We will then take fx in fx expression for fx, we will take, instead of root 2 over pi, 2 over pi. So so let us say that f c omega, let us take the definition of f c omega as 0 to infinity fx cos omega x dx. Okay. So if you compare with this, it is e to the power minus omega. Now let us find the inverse formula. So 2 over pi 0 to infinity f c omega cos omega x d omega. Okay. So this is 2 over pi 0 to infinity e to the power minus omega cos omega x d omega. Let us take I equal to 0 to infinity e to the power minus omega cos omega x d omega. Then I can write it, we can integrate by parts. So e to the power minus omega sin omega x over x 0 to infinity minus 0 to infinity minus e to the power minus omega and sin omega x over x d omega. Okay. So when omega goes to infinity, e to the power minus omega goes to 0, while sin omega x is a bounded function and therefore product goes to 0, and when omega is 0, sin omega x is 0, so the first expression becomes 0, this minus becomes plus 0, and when we write 1 over x outside, but we have 0 to infinity e to the power minus omega sin omega x d omega. So again we integrate by parts. So e to the power minus omega, integral of sin omega x is minus cos omega x divided by x 0 to infinity minus 0 to infinity minus e to the power minus omega minus cos omega x divided by x d omega. Now when omega goes to infinity, e to the power minus omega goes to 0, cos omega x is bounded by 1, so the product goes to 0, and when we put the lower limit, what we have, e to the power minus when we put omega as 0, this is 1 and this is minus 1 over x, so we get plus 1 over x, then we have this becomes minus, so we get minus 1 over x integral 0 to infinity e to the power this 1 okay, so e to the power minus omega cos omega x d omega. So this is 1 over x square times 1 minus I. Okay. If we do not, we have denoted 0 to infinity e to the power minus omega cos omega x d omega as I. So 1 over x square into 1 minus I we have. Okay. So what we have, let us take this term to the other side, then I times 1 plus 1 by x square we have equal to 1 by x square. So, this gives us I equal to 1 upon x 1 plus x square. Okay. So, what we have here f x equal to 2 over pi into 1 plus x square. So, we can solve the integral equation by using Fourier cosine transform. So, f x is 2 over pi 1 into 1 plus x square. Now, integral transforms are used to find the solution of a partial differential equation. The choice of a particular transform to be used for the solution of the differential equation depends upon the nature of the boundary conditions of the required problem, and the facility with which the transform f w can be inverted to give f x. Let us assume that in the problems that we consider, the u x t function which depends on the space variable x and time t and its derivative with respect to x, that is gradient, be functions which tend to 0 as x goes to plus minus infinity, then the Fourier transform of u x x is given by this. So, let us see how this Fourier transform we are getting. Let us go to the definition of the Fourier transform. Fourier transform be defined as 1 over root 2 pi minus infinity to infinity f v cos f v e to the power minus I omega b dv. So, let us use this definition. Okay. So, f of u x x, let me do here. So, Fourier transform of u x x, this is equal to 1 over root 2 pi integral over minus infinity to infinity e to the power minus I omega x dx. Okay. So, when we integrate by parts, what we get? Integral of this second order derivative becomes first order derivative into e to the power minus I omega x minus infinity to plus infinity, then minus infinity to plus infinity into minus I omega e to the power minus I omega x dx. Now, let us see, we have assumed that this u x, goes to 0 when x goes to plus minus infinity, and let us remember that e to the power minus I omega x, modulus of this is equal to 1. So, it is a bounded quantity. So, when u x goes to 0 when x goes to infinity and u x goes to 0 when x goes to minus infinity, because of the boundedness of e to the power minus I omega x, this part becomes 0, and what we get is then 1 over root 2 pi I omega times integral 0 minus infinity to infinity u x into e to the power minus I omega x. Let us integrate once more. So, 1 over root 2 pi I omega, when we integrate once more, we get u into e to the power minus I omega x minus infinity to infinity, and then minus infinity to infinity u times minus I omega e to the power minus I omega x dx. So, but again e to the power minus I omega x is bounded, u goes to 0 when x goes to plus minus infinity. So, this part goes to 0 and this becomes then minus minus plus I omega comes outside, it becomes I square omega square. So, we get minus 1 over root 2 pi omega square minus infinity to infinity u times e to the power minus I omega x dx. Okay. So, minus omega square times u omega t, this is nothing but minus u square minus omega square times Fourier transform of u function. Okay. So, f u x t, which we are denoting by u omega t. So, minus omega square u omega t. So, Fourier transform of second derivative of u with respect to x is replaced with minus omega square u omega t in the problems. Similarly, us omega t represents Fourier sine transform of f x, uc omega t represents Fourier cosine transform of the function f x, okay. And let us denote, so then us omega t is 0 to infinity ux t sine omega x dx, where we are taking this coefficient instead of root 2 over pi as 1. Then f s uxx becomes omega uxt at x equal to 0 minus omega square us omega t. And similarly, for the Fourier cosine transform, if you find the Fourier cosine transform of uxx, it becomes minus ux at x equal to 0 minus omega square uc omega t. Here again, like we use the boundedness of e to the power minus I omega x here to make this term 0, there also, because of instead of e to power minus omega x, we will have sin omega x and cos omega x. They are bounded quantities, they are bounded by 1. So, we will see that this expression again in the case of sin omega x and cos omega x goes to 0. So, we can easily prove this formulas. Now, in one dimensional problems, the PD is transformed into an ODE by applying a suitable transform. If in a problem uxt at x equal to 0 is given, you see here in this formula, when you take Fourier sine transform of this uxx, you are having the expression as omega into uxt at x equal to 0, while in the case of Fourier cosine transform, you have minus delta u over delta x at x equal to 0. So, if in a problem you have uxt at x equal to 0 is given, then you use Fourier sine transform. If in the problem the boundary condition is given as minus delta u by delta x at x equal to 0, then you use Fourier cosine transform. So, which the transform that is to be used depends on the given boundary conditions. Now, let us look at this problem. Determine the distribution of temperature in the semi infinite medium x greater than or equal to 0 when the end x equal to 0 is maintained as at 0 temperature, and the initial distribution of temperature is f x. So, we have this equation. We have del u by del t equal to c square delta square u by delta x square. Now, the boundary condition here is that at x equal to 0 temperature is 0. So, u 0 t is equal to 0 for all the time t, and we are given initial temperature distribution as ux 0 equal to f x. Now, you can see we are given uxt at x equal to 0. When uxt at x equal to 0 is given, we use Fourier sine transform. So, let us take the Fourier sine transform of the given equation, this one. Okay. So, taking Fourier sine transform means you multiply both sides with sin omega x and then integrate with respect to x. Okay. So, delta u by delta t into sin omega x dx, and we integrate over 0 to infinity. Right side will be c square times integral over 0 to infinity delta square u by delta x square sin omega x dx. Okay. Now, if x and t are independent variables, so here integration is with respect to x. So, I can write this also as this is Fourier sine transform of uxx, and we can then use the formula c square times Fourier sine transform of uxx. We have seen it is minus omega uxt at x equal to 0 minus omega square us omega t. So, we can put the value omega times uxt at x equal to 0 minus omega square us omega t. Okay. uxt at x equal to 0 is given, it is 0. So, we get here c minus c square omega square us omega t. Okay. And left hand side is what? This is us omega t. Left hand side is this. So, that we have plus c square omega square us omega t. Now, it can be treated as a first order differential equation du by dt plus c square omega square u, and then its solution will be du by u. So, ln u ln us omega t is equal to minus c square omega square into t plus some constant. Now, because it is partial derivative, the constant of integration will depend on omega. So, we can call it as a omega, okay, ln a omega. So, then us omega t will be equal to as into e to the a omega into e to the power minus c square omega square t. Now, at t equal to 0, ux 0 equal to f x. Let us look at this. So, from here we have us omega t equal to 0 to infinity. We have taken ux t into sin omega x dx. This we defined, hai na? So, we put t equal to 0 in this, then us omega 0 equal to 0 to infinity ux 0 sin omega x dx, and this is nothing but 0 to infinity ux 0 equal to f x. This is Fourier transform of f s f x. So, I can write it as f s omega bar. Okay. So, what we will have, we put t equal to 0. So, us omega 0 equal to a omega. Okay. Us omega 0 is f s bar omega, okay, Fourier sine transform of f x. Okay. So, then thus us omega t becomes f s bar omega into e to the power minus c square omega square t. Now, let us use the inversion formula for the Fourier sine transform, because here we are taking one coefficient. Okay. Now, while inverting we will take 2 over pi. So, we multiply both sides by sin omega x, integrate over 0 to infinity with respect to omega and multiply by 2 over pi. So, 2 over pi 0 to infinity us omega t into sin omega x d omega equal to 2 over pi 0 to infinity f s bar omega e to the power minus c square omega square t into sin omega x t omega. Okay. Now, left hand side is f x, and so we get this result f x. So, left hand side is u x t. Okay. Left hand side is the inversion formula for u x t. So, left hand side is u x t. So, u x t is equal to 2 over pi integral 0 to infinity f s bar omega e to the power minus c square omega square t into sin omega x d omega. So, this is how we solve this boundary value problem. With that, I will like to end my lecture. Thank you very much for your attention.